Hi, my name's Kennedy, and today I'll be talking about the electromagnetic spectrum. To start off, we will talk about wavelengths, frequency, and the speed of light. Light travels nearly 1,000,000 times faster than sound, just to put things into perspective. Light's color is determined by wavelength, the length between the two crests of a wave. The amplitude or height of a wave determines the intensity of the light, so whether it is bright or it's dark. Frequency is also a characterization of light. The number of wave crests that pass through a stationary point in a given time determines the frequency. This is measured by cycles per second in hertz. Frequency is proportional to the speed at which a wave is traveling. The faster the wave, the more crests that pass through a certain location per unit of time. There is an equation to help us determine frequency. Frequency equals the speed of light, c, divided by the wavelength. As I described before, this is the wavelength calculation. Wavelength equals speed of light divided by frequency. This problem we will try together. Frequency is given at 100 nanometers. Speed of light is 3.00 times 10 to the power of 8 meters per second. Now we will calculate it. As you can see, I put the equation above. Frequency equals speed of light over wavelength. The frequency is 100 nanometers equals 3.00 times 10 to the 8 meters per second for speed of light. We divide by the speed of light on both sides to get the wavelength, and our wavelength becomes 0.0000003 repeating seconds. Now you try. The speed of light is 3.00 times 10 to the 8 meters per second, and the frequency to solve for is 4.62 times 10 to the 14. For this equation, we're asked to find the wavelength. We put 3.00 times 10 to the 8th meters per second over 4.62 times 10 to the 14th seconds. We cancel those out, divide, and we get 6.49 times 10 to the negative 7 meters. 6.49 times 10 to the negative 7 meters, and we convert into nanometers, and you get 649 nanometers. In relation to the electromagnetic spectrum, we can correlate frequency, wavelength, and energy. For example, the shorter the wavelength, the higher the frequency, the higher the energy. In reverse, when the wavelength is longer and the frequency is shorter, the energy is therefore shorter. Here's a diagram of the electromagnetic spectrum. Energy increasing is on the top towards the left. The wavelengths get shorter to the left, and then our frequency is closer to the bottom near the visible light. Now I'm going to explain the shortest wavelength. If you look right in the middle, you'll see gamma rays first. Gamma rays are the size of an atomic nuclei. Gamma rays are the shortest wavelength. They are produced by the sun, stars, and other unstable nuclei on Earth. Excessive exposure is really dangerous. The next one we will talk about is X-rays. X-rays have a little bit longer of wavelength. X-rays make up X-radiation, a form of high-energy electromagnetic radiation. Most X-rays have a wavelength ranging from 0.1 to 10 nanometers, corresponding to frequencies in the range of 10 petahertz or 30 extrahertz, and energies in the range of 100 eV to 200 keV. X-rays are a photographic or digital image in the internal composition of something, especially a part of the body, produced by X-rays passing through it and being absorbed to different degrees by different materials. With imaging of bones and internal organs, too much exposure of X-rays can cause cancer. The main difference between X-rays and gamma rays is that gamma rays are produced during nuclear decay by nuclei of atoms, whereas X-rays are produced by electrons. For instance, for medical purposes, X-rays are produced by accelerating some electrons and then making them collide with a metal target. Next, I will be discussing ultraviolet radiation, or UV radiation. UV radiation is divided into three main groups. UVA radiation have the least energy among UV rays. UVB rays have slightly more energy than UVA rays. And lastly, UVC rays have more energy than the other types of UV rays. Ultraviolet radiation is a form of electromagnetic radiation with a wavelength from 10 nanometers to 400 nanometers, shorter than that of visible light but longer than X-rays. UV radiation is present in sunlight and constitutes about 10% of the total electromagnetic radiation output from the sun. It is also produced by electric arcs and specialized lights such as mercury, vapor lamps, tanning lamps, and black lights. Ultraviolet radiation can cause you to tan and even sunburn. It can be very damaging, causing skin cancer, eye cataracts, and early aging and wrinkling of the skin. Your sunlight destroys bonds in your body, and you need to be careful. Now I'm going to talk about visible light. For visible light, it is light that can be seen by the human eye. Wavelength determines color. White light is the rainbow of colors we can see when passing through a prism or a rainbow in the sky. Red light has the longest wavelength of visible light from 750 nanometers. Violet has the shortest of 400 nanometers. The light we see is the light that's being reflected. For example, if you see a red shirt, all the other colors are being absorbed and red is being reflected, and that's why you can view that color. In this image taken by National Geographic, we can see all the colors of the spectrum. Although visible light cannot harm your body, it can cause changes to your eyes and send signals to the brain that help you see. Next on the spectrum, we see infrared radiation. Infrared radiation, sometimes called infrared light, is electromagnetic radiation with wavelengths longer than those of visible light. It is therefore generally invisible to the human eye, although IR waves up to 1050 nanometers from specifically pulsed lasers can be seen by humans under certain conditions. IR wavelengths extend from nominal red edge to the visible spectrum at 700 nanometers to 1 millimeter. Infrared radiation carries radiant energy and behaves both like a wave and like its quantum particle, the photon. The heat you feel when you touch the stove can be related to infrared radiation. Human bodies also emit infrared radiation. Night vision technology can detect this light. Microwaves are used for radar and in microwave ovens. Although microwave radiation has the longest wavelengths and therefore lower energies than visible or infrared light, it is efficiently absorbed by water and can therefore heat substances that contain water, such as vegetables. Microwave energy is changed to heat as it is absorbed by food and does not make food radioactive or contaminated, and therefore the food heated by microwaves is okay to eat. Lastly, I will be talking about radio waves. Radio waves travel at the speed of light. They are generated by electric charges undergoing acceleration, such as varying electric currents. Naturally occurring radio waves are emitted by lightning and astronomical objects. Some types of radio waves are transmitting signals responsible for AM and FM radios, cell phones, and TVs. Now to close, I'll ask a few questions. Which of the following is the correct order of highest to lowest energy? A. X-rays, visible light, microwave. B. Ultraviolet, visible light, gamma rays. C. Microwave, visible light, gamma rays. The correct answer is C. Microwave, visible light, gamma rays. The photons that make up radio waves travel at the same speed that make up visible light. A. True. B. False. The correct answer is A. That is true. Hopefully my presentation taught you something about the electromagnetic spectrum that you didn't know. Thank you for watching.